Hello everyone. Under digital signal processing, we'll be talking about DTFT. DTFT, that's the subtopic. Now, when we talk about DTFT, what should come to your mind? The first thing that should come to your mind is, what does DTFT stands for? DTFT basically stands for what? Discrete time Fourier transform. Discrete time Fourier transform. So basically, your D here simply stands for what? Discrete. Your T stands for what? Time. Your F here stands for what? Fourier. And the last T stands for what? Transform. So basically, we are not using this long word, but we are using what? DTFT to represent what? Discrete time Fourier transform. Now, when we talk about DTFT, our major interest will be on what? Signals, because we are talking about digital signal processing. So our interest will be on signals. So basically, we have two categories of signals, and what are they? The first category of signal is what? S bracket what? N, and the second category is what? S bracket T. Now, basically, these are two categories of signals. This is what? This is a discrete signal, and this is a what? A continuous signal. Now, when we are talking about discrete signal from the word DTFT, we know that DTFT basically stands for what? Discrete time Fourier transform. Now, this signal is a discrete time signal. So basically, when we are talking about DTFT, this is the signal we are interested in, this signal, and not this signal. Now, this signal, on the other hand, is a continuous time signal. And continuous time signal is an example of an analog signal. Remember, we are not talking about analog signal, but we are talking about what? Digital signals. So our interest is not what? Our continuous signal. Now, but if you want to talk about this continuous signal, what you will be talking about here is what? CTFT. CTFT. Now, what's CTFT? CTFT simply stands for what? Continuous time Fourier transform. And when you apply CTFT to a continuous time signal, you simply arrive at what? You simply arrive at a continuous spectrum. Continuous spectrum. But this is not our interest. Our interest is not what? CTFT. Our interest is what? DTFT. So you have this signal, discrete time signal, and you apply DTFT. What should be your answer? Let's drive out the concept of DTFT. Let's drive out what? The concept of what? DTFT. Now, this is a discrete signal. This is a discrete time signal. If you apply DTFT to this discrete time signal, what do you think your answer will be? Now, this is S of what? N. You know this as a discrete signal. If you apply a DTFT to this signal, you arrive at what? S bracket what? Omega. Now, this signal here is what we call the frequency domain. This part is what we call the frequency domain. And this part is what we call your time domain. So basically, you have your what? Your time domain. And this part is called your what? Your frequency domain. So basically, our interest is what? Two paramount things. And what are they? Your time domain and your frequency domain. So when you apply a DTFT to a signal, the first thing that should come to your mind is, I'm going to get something. And what is that? Frequency domain. Are we together? Now, this is the first concept. The first concept was applying what? DTFT to get your what? Your frequency domain. What if you want to take this signal from frequency domain to time domain? What do you do? Now that will give us the second concept, which says what? Taking your frequency domain back to your time domain, you apply what? Inverse DTFT. Remember, this was our what? Our concept 1. This is our concept 1. Now, our concept 2 says what? Convert your signal from frequency domain back to time domain. What do you do? I told you, when you want to convert your frequency domain back to your time domain, you apply what? Inverse DTFT. Inverse DTFT. Now, in this case, your inverse DTFT is written as what? I dot what? DTFT. So if you see I dot DTFT, you know that this is what? Inverse what? DTFT. Are we together? So if you have this frequency domain, the second concept 2. Now, concept 2 is telling us what? We have SW to be our what? Frequency domain. We want to apply what? I dot DTFT Now, if you apply I dot DTFT, you simply what arrive at your what your time domain. Are we together? So here you are converting your what your frequency domain back to your time domain. And what do? You apply what inverse what DTFT. Now take this down. Note your frequency domain is denoted in two ways. Now this is the first denotation. This is the first one. We have S bracket what W, S bracket omega. Now you can see this, or better still, you can see S bracket what EJW. So if you don't see this, you can see this. If you don't see this, you can see this. So these two are the ways to represent what frequency domain. So in that case, we can still use our first concept to be what S bracket N applying what DTFT to give us what S bracket EJW. Are we together? Now this is what your first concept. Here we are using what the second what denotation, but here we use what the first denotation. Are we together? So now if you don't want to use this, you will use this. So let's use the second concept to represent what we have here using what IDTFT. So basically we still have something like S bracket EJW applying what inverse DTFT. And if we apply inverse DTFT, we arrive at what our time domain, which is S bracket N. Are we together? Basically what we've been talking about the concept of what DTFT. We've gotten the first concept and the second concept. Now what should come to your mind is, when getting the first concept, what equation are you supposed to use to get your frequency domain? Are we together? Now if you have your concept one was S bracket N applying what DTFT to get your what frequency domain, or S bracket EJW. These two are what our frequency domain. That's our first concept. Now what's the formula that will guide you? What's the formula that will guide you in getting what your frequency domain perfectly? Now note, what we want to get, our interest is what our frequency domain. So the formula for frequency domain is simply what S bracket what W is equal to summation of what N is equal to minus infinity to what infinity. What is our interest? This, but what we have here is what S bracket what N multiplied by exponential minus what JWN. Now this equation will help you in getting your frequency domain. Are we together? Where your time domain will be given to you, and you put your time domain here. Your infinity signs, they will give you your boundary conditions. You input your boundary condition and you get your frequency domain. Are we together? Now remember, this equation is similar to what Z transform. For those of us that have done Z transform, this equation is similar to Z transform. Now what is Z transform? Z transform equation is simply what summation of what N is equal to minus infinity to what infinity time domain multiplied by what Z minus N. Now look at this equation. This equation is for what? This equation is for what? Z transform. Our interest, recall, our interest is not Z transform, but want to drive out something. Are we together? Now this equation is similar to what we have here, DTFT equation. Now what's the difference? The difference is what? E minus what? JW. What do you have here? This one is happening as Z minus what? N. So if you remove this and you put this in this equation, you will simply what? Get the DTFT equation. Are we together? Now recall, this is not our interest. Z transform is not our interest. I was just telling you that this equation is similar to Z transform. In case you don't remember this equation, you can remember Z transform equation and you remove what? Z minus N and you input what? EJ what? EJW. Are we together? We've gotten the equation for what? Frequency domain. We've gotten the formula to calculate for what? Your frequency domain when you apply DTFT. Remember, this is our what? First concept. Now let's take the second concept where you apply what? I dot DTFT, which is inverse of DTFT. You convert your frequency domain back to your what? Your time domain. So concept 2. For concept 2, what's concept 2? Concept 2 was what? Your frequency domain back to your what? Your time domain. Applying what? DTFT. Are we together? So you have what? S bracket what? N. Now here the formula the formula I will give to you is the formula of what? Time domain. Are we together? Here we got what? The frequency domain. That's our interest. But in the second concept, the formula, our interest is what? Time domain. Are we together? Now time domain equation is simply what? 1 over what? 2 pi integral of what? Minus pi to what? Pi. Our interest here is what? Frequency domain multiplied by exponential JWN. We are integrating with respect to what? The W. Are we together? So now this equation is applicable when we are converting what? Your frequency domain to time domain, applying what? Inverse DTFT. So basically we've gotten two formulas. The first formula was for what? Frequency domain, and the second formula was for what? Time domain. So if you are asked to apply your two concepts, first thing you note is what? Remember, when talking about DTFT, two paramount things are what? Are being what? Noted. What are they? The time and the frequency domain. Are we together? Now you check your question. If you are asked to what? Apply what? Inverse DTFT. What's the concept to use? Remember the second concept and you apply what? Your second formula. If you are asked to apply what? DTFT, remember your first concept and you apply what? Your first equation. Are we together? Now somebody will ask me, why then we study what? DTFT? Why do we study what? DTFT? The major reason why we study DTFT is to what? Is to get what? The magnitude and the phase of a signal. I told you what? To get what? The magnitude. Our interest is what? Magnitude. And the second one is what? Is the phase of a signal. Is the phase of a signal. Are we together? Now, basically, your frequency domain is always characterized in two forms. Your frequency domain, this is your frequency domain. Your frequency domain is characterized in two forms. Now, what are they? The first form is what we call the polar form. S bracket W, which is our frequency domain, is characterized in two forms. The first one is what we call the polar form. And the second one is what we call the rectangular form. Now, when you are giving your polar form and when you are giving your rectangular form, what should come to your mind? Magnitude and what? Phase. You are to get what? The magnitude of that signal and the phase of that what? Signal. Are we together? So now, how do you know if your signal is given in what? In polar form? How do you know if your frequency domain is given in what? In polar form? And if you have the signal in this manner, now, if your signal is given in this manner, what should come to your mind? There are two things that are very important. What are they? The magnitude and what? The phase. That's why we study what? DTFT. Now, from our elementary maths, we know that from vectors, when we talk about absolute, we are talking about what? Magnitude. When we talk about absolute. So if you have what? In vectors, if you have A absolute, this is what? The magnitude, to get the magnitude of what? A. Now, apply the same concept here. Basically, this is our magnitude. This is our magnitude, and this is our phase. So here you already know what? You already know your magnitude, and you already know what? Your phase. Are we together? So basically, if you are given your form like this, the first thing you do is recall our concept of vector, absolute value, magnitude. Apply it here, absolute value, magnitude. The last one we have here is your phase. Are we together? Now, how do you know if your signal is given in rectangular form? Now, if you have a signal in this manner, rectangular form. Now, if you have a signal, rectangular form signals are always given in this manner. S bracket W is equal to S subscript RW plus JXIW. Now look at this. You can see that what you have here is not the same form with what you have here. Basically, what you have here is similar to what is A plus what? JB. Now, when you see something like this, what do? You know that this part is what we call real part, and this part is what we call imaginary part. Apply this to this. Apply this to what we have here. We simply have our real part and our imaginary part. So basically, when you are giving your form in rectangular way, when you are giving your signal in rectangular form, they will give you that signal in what? Real form and what? Imaginary form. Now, it's left for you to what? from your real form and imaginary part to get your what? Your magnitude and your phase. That is our interest. I told you magnitude and phase is our interest when we are talking about what? Frequency domain. So now, how do you get your what? Your magnitude and the phase of that what? Signal. Now, for you to get the magnitude of this signal, what you do is what? Square both of them, then take the root of what you have here. Now, you have what? The square root of what? SRW square plus the square of what? JSW all square. Now, this is your square of your real part. This is the square of your what? Your imaginary part. Now, this is the what? The magnitude of your what? Your rectangular form. Now, this equation, this formula will help you to get what? The magnitude of your what? Of your rectangular form. Are we together? Now, the next thing we'll consider is what? The phase of the signal. How do you get the phase of the signal? Basically, when we talk about the phase of the signal, when we have the real part and the imaginary part, what we introduce is what we call the tan inverse. So you take the tan inverse of what? Of your imaginary part divided by your real part. Now, for you to get your phase, what's your phase there? SW. Are we together? So your phase is what? You introduce what? Tan inverse of what? Your imaginary part, SIW, divided by your real part, SRW. Are we together? So now this will help you to what? To get your what? Your phase. This will help you to get your what? Your phase of what? Your rectangular form. And this formula will help you to get what? The magnitude of your rectangular form. Are we together? In conclusion, we talked about what? DTFT, where I gave you the first concept. The first concept was what? Converting your what? Your time domain to frequency domain. We also talk about the second concept, which is here. Look at what we have here. The second concept. The second concept was what? Converting your frequency domain back to your time domain. And see the formulas applicable when we're talking about what? When we talk about what? DTFT. Are we together?